Let's look at an example where you can use left sums and right sums to estimate the area underneath a curve. A classic problem is to compute the area of a circle. Here we have a circle, well, a quarter of a circle anyway. This is the unit circle, meaning it's centered at 0 and has radius 1. So the equation of the circle is x squared plus y squared equals 1. We know how to find the area of a circle. It's pi r squared, which in this case is pi times 1 squared, which is pi. But of course, what we're looking at here is a quarter of a circle, so we need to divide all of this by 4. So pi over 4 is the area of this region. We know that because we have a formula. But suppose we didn't have a formula. Suppose no one had given us a formula. How would we estimate the area of a circle? Well, one way to do it is using left sums and right sums. So how do we go about doing that? Well, we draw a picture. We have a picture here. The benefit of looking at the top half of the circle instead of the whole circle is that you can write an equation which will give you a function. What do I mean by that? If you solve for y, you have y squared equals 1 minus x squared, and then you look at the square root. Y is the square root of 1 minus x squared. This is an equation, but it's an equation that defines a function. F of x equals the square root of 1 minus x squared. So we have a function, and now we can find the area underneath that curve using left sums and right sums. All right, so how do we choose how many rectangles that we want to use? Well, there's nothing here at the moment that is dictating how many we use. So we can start with a simple, easy number like 4. So try n equals 4. I picked that number because it's very convenient with the grid that I have here. If n is equal to 4, then delta x is going to be 1 over 4. That is to say, all of these subintervals have length 1/4. Now, how did I know that? Because the total length is 1, and I'm dividing it into 4 pieces. So this is 1/4, this is 2/4, which is 1/2, and this is 3/4, and finally we have 4/4, which is 1. I can do left sums or I can do right sums. Let's start with left sums. Let's do L sub 4. Now, if I'm doing L sub 4, then I need to look at the left endpoint. So my first interval goes from 0 to 1/4. The left endpoint is 0. And so the height is just slightly above the circle, like so. So L4 is going to be equal to, well, what is the height of this? The height of this is 1 times the width, which is 1/4, plus my second interval. Again, my interval is from 1/4 to 1/2, so I use the left endpoint, which is 1/4, and that intersects the curve right here. That dictates the height of the rectangle, like so. Now I know what the width is. The width is 1/4, but what is the height? Well, the height is given by the function. So this point right here has height f at 1/4. And we can compute that. F at 1/4 is equal to the square root of 1 minus 1/4 quantity squared. We could simplify that, but I'm not going to. I'm just going to leave it like that. So it's the square root of 1 minus 1/4 quantity squared. And I'm going to multiply this by delta t, which is 1/4, or delta x rather, which is 1/4. Plus, there are a total of 4 intervals, so I need 4 terms. The next interval goes from 1/2 to 3/4. I use the left endpoint, which is 1/2, and that intersects the curve right here. That determines the height of the rectangle. So again, to find the height of this rectangle, I just evaluate f at the left endpoint. F at 1/2 is equal to the square root of 1 minus 1/2 squared. So I add that in. Square root 1 minus 1/2 squared, and again this is times 1/4. Well, there's one more interval, the interval from 3/4 to 1. So again, I use the left endpoint, which is 3/4, to determine the height, which is going to be like so. And this height is f at 3/4. And just like the others, f at 3/4 is equal to the square root of 1 minus 3/4 quantity squared. So that's going to give me my fourth term. So it's plus the square root of 1 minus 3/4 quantity squared. And again, this is times 1/4, just like the others. Now this is the thing that I want to compute in order to get my sum. Now this is not the kind of thing that I can do in my head, but I can easily do it using a calculator or a computer. L4 is equal to the sum. If I use summation notation to make this easier to write, it's going to, all of the terms look like the square root of 1 minus something. And what is that something? Well, it's always going to be something over 4 quantity squared. And all of these things are multiplied by 1/4. Now the thing inside the parentheses is something over 4, and I can just put a k there. And the k goes from 0 to 3. When k is equal to 0, this term disappears, and that gives me this 1. Then I have k equals 1, and that's this term right here. K equals 2 is 2/4. 2/4 is 1/2. And then finally, when k equals 3, I have 3/4. The advantage to using summation notation is it's a lot easier to write down, and also if you want to use a computer to compute it, this is the kind of form that you need it to be in. If I do this on a computer, I should get some answer like 0.873927. And that's my left sum. Now notice that this is a decreasing function on the interval from 0 to 1, so all of my rectangles are just slightly too big for the curve. That means I have an overestimate. That's because the function is decreasing and I'm using the left sum. If I use the right sum, then all of the rectangles will be underneath and I'll get an underestimate. So let's do that now. So R4 is going to be equal to, well, again, there's going to be 4 rectangles, but now I'm going to use the right endpoints. So the first interval from 0 to 1/4, the right endpoint is 1/4. So that's going to determine the height of my rectangle, like so. From 1/4 to 1/2, 1/2 is the right endpoint, so that determines the height of the rectangle. From 1/2 to 3/4, 3/4 is the right endpoint. Now finally, on 3/4 to 1, 1 is the right endpoint. So that means the height is going to be 0 on this last one. So you can see that this is going to be an underestimate that's quite under the actual value, because I'm not including any of the rightmost rectangle in my sum, or at least none of the circle is included in that. So this will be too small for sure. So what does this look like if we add it up? Well, again, all of these have width 1/4. And so all of their heights are determined by the function values. The first one has height f at 1/4. So I'm just going to write down f at 1/4 for the time being. And this, of course, is multiplied by delta x. So let's just write delta x, just to make it easy. The next one is f at 1/2 times delta x, plus f at 3/4 times delta x, plus f at 1 delta x. So notice that all of these things, all of these numbers are the right endpoints, because I'm doing r sub n, where n is equal to 4. So 1/4, 1/2, 3/4, 1. Those are the numbers that appear here. Now all of these have delta x, so there's no reason I can't just factor out the delta x. So I can write this as f of 1/4 plus f of 1/2 plus f of 3/4 plus f of 1, and all of this is times delta x. Well, we can actually compute these things. So the first one is the square root of 1 minus 1/4 squared, plus the square root of 1 minus 1/2 squared, plus the square root of 1 minus 3/4 squared, plus, and this next one is 1 minus 1 squared, so that's going to be 0. And all of this is times delta x, which is 1/4. So that's 0. So if you compute this, you should get that R4 is approximately 0.623927. So our actual area, which we know is pi over 4, is somewhere between 0.873927 and 0.623927. If we want to have some idea of how good our approximation is, or our two approximations are, we can always measure the distance between these two numbers. We know that pi over 4 is between the two, so pi over 4 is going to be closer to 0.623927 than the upper bound of 0.873927 is to 0.623927. And we know what the distance between those two is, so if we do L4 minus R4, that's 0.873927 minus 0.623927, this is just 1/4. So that means either one of these estimates is within 0.25 of the actual value of pi over 4. Now, that's not a coincidence that it's 1/4, because we know how to compute the error, or at least a bound on the error. So our error bound is equal to the absolute value of L4 minus R4. Now, when I say that we have an error bound, that's because this is a decreasing function. And if you have a decreasing function, then you know the error is always going to be is going to be smaller than this distance. That's because you know that one is an upper bound and the other is a lower bound. So that means the actual value is necessarily between the two. And since you know that it's between the two, that means you can measure the distance from either one and say that it must be smaller than the distance between the two, L4 and R4. And this is something that you can easily compute without actually doing any of the computations, because what are these numbers? L4 is going to be f at the first one, which is 0, plus f at the second endpoint, which is 1/4, plus f at 1/2, plus f at 3/4. All of this times delta x. And then from that, I want to subtract R4. Now, R4 is very similar, but it starts at 1/4, and then it's f at 1/2, and then it's f at 3/4, and then finally it's f at 1. All of this is times delta x. So if you want to compute the difference between these, there's a lot of terms in common. The 1/4 cancel, the f at 1/4 cancel, the f at 1/2 cancel, the f at 3/4 cancel, and you're just left with f at 0 minus f of 1 times delta x. Now, we usually put absolute values around these just to make sure that everything's positive. But we actually know what these values are. We know what all of this is. F of 0 is 1, f of 1 is 0, and delta x is 1/4. So this is just going to be 1 minus 0 times 1/4, which is 1/4. The important thing is that it's delta x. So whatever my delta x is, that dictates how close my L4 and R4 are going to be to the actual area. So if I want to have a better estimate of pi over 4, I need to pick a much bigger n. Pick larger n, because delta x is b minus a over n, which is 1 minus 0 over n, which is 1 over n. So in this case, our ln minus rn is equal to 1 over n. So by choosing n really large, you get this error bound to be really small. So if I want ln and rn to be really close, so let's say within 1 over 100 of pi over 4, I need to pick n equals 100. Now that's not the kind of thing I can do by hand, but I can easily get a computer to do that. And I can still write it out in summation notation. So L sub 100 is going to be equal to the sum, and here I'm using left endpoints. So I'm going to start at x0, which in this case is going to be, so we're going to have the square root of 1 minus k over, not 4 this time, but 100, quantity squared, times 1 over 100. And I'm going to start with k is equal to 0, and I'm going to go to k equals 99. So that's going to give me 100 terms, starting at 0 and going to 99. Now again, I can't compute that by hand or in my head, but I can get a computer to do it. And R100 is the sum 1 minus k over 100, quantity squared, times 1 over 100. But now I'm using the right endpoints. So I'm going to start at 1 and go to 100. Now I don't need to know exactly what this looks like, but the idea is that you have 0 over here and 1 over here, and you're going to divide this up into 100 little pieces. And the first little piece is 0, 2, 1 over 100, and then 2 over 100, and so on and so forth until the very last couple here are going to be 99 over 100, and the last one is 100 over 100, which is 1. The width here of all of these is 1 over 100. That's my delta x. So the usefulness of this little diagram is that it makes sure that we start at the right endpoints. So if we're doing L sub 100, we start at the left endpoint, which is 0. And the last interval, the left endpoint, is 99 over 100. So that's where that 99 comes from. And similarly, if I'm doing the right endpoints, I know that the first interval, the right endpoint is 1 over 100. So that's why there's a 1 there. And the last, of course, is 100 over 100. So that's why we have a 100 that we're going to in R sub 100. Now, once again, I can't compute these by hand, or at least I don't want to compute these by hand, but I can easily do it with a computer. In fact, I've already done these by computer, and what I got was L100 was approximately equal to 0.790104, and R sub 100 is approximately equal to 0.780104. Now the actual value of pi over 4, well, I don't know the actual value, but I can approximate that using a computer as well, and I get something like 0.785398. So you can see that L100 is just slightly bigger, and R100 is just slightly smaller. Now in this particular case, because I have a decreasing function, I know that the left sums are always bigger and the right sums are always smaller. So if I want to even get a better approximation, what you can do is you can average it. So L100 plus R100 over 2 is approximately equal to 0.785104, which as you can see is even better than L100 or R100. Now that only works because this was a decreasing function. It would also work if you had an increasing function, but that's because we know the actual value is always between L and R. L sub n and R sub n are always either too big or too small, and so the average is somewhere in between, just like the actual value.